So my name is Teresa. I run the Full Stack Data Science Lab in Fort Collins, Colorado. I'm a part of the HPE Labs AI Lab team. And what this lab does is it's pretty much split up into two parts. We have an actual model development lab, which is based out of Grenoble, France. And then we have the Full Stack Data Science Lab, which is my lab in Fort Collins. We work with extreme scale accounts. So these are people with exabytes of data or exabytes of ingest. So typically we are working to solve one of two problems. Either they are ingesting terabytes a second and they need to know how to store it all, or they are ingesting terabytes a second and they only want to store maybe 20% of that. Both of these are NP hard problems, and that's what we specialize in. We do full end-to-end pipeline development. We pick the right tools for the problem. Nearly every single performance requirement that comes in has microseconds of latency to single-digit milliseconds on the real-time inference tier. So to do full-stack data science development, you have to work across the organization. It starts with the executive level. So it's the C-suite that defines business problems. And we work with the executives to figure out a business problem that can be quantified and solved through technology within 18 months to 2 years. It has to be able to generate some kind of ROI in that time frame. If it can't, it's too complicated. They don't understand the problem. We don't understand the problem. There's a gap. So that's pretty much how it works. Everything is very, very specific, and it's intended to solve a very specific problem. Data is a huge problem anymore. Because we specialize in global clients, you have to know laws from all over the world. What is considered ownership here over data, in an Asian country, there is no such thing. So you have to be mindful of the culture, of the laws, where's the data going to reside, and you have to be able to deal with the ethics around data, which very well could translate to a legal issue. So all of these problems have to be built right into your data science stack, whether people realize it or not. If you don't think about that up front, it will bite you in the end. So a lot of the accounts that I work with are confidential. We can't talk about their data. But one of the things that we do for the sake of the public good is astrophysics. So astrophysics is most of it is public. They have very large public data sets. A lot of their code is public. Anybody can go out there and improve those programs. And so this is a real passion of mine specifically. So if you think about CERN right now, the Large Hadron Collider out there in Switzerland and France, right now its data set is hovering just under 1 exabyte of data. Once they get their big upgrade done, which is going to be the HL, so the High Lumen Hadron Collider, that is expected to grow 60 exabytes annually. So it's going to be massive. 5 terabytes of data per second is what is estimated. And the new SKA array, which is a giant aperture array that's being installed in Australia and South Africa, has the same type of data problem. Once it's fully online in 2028, it's expected to ingest somewhere around maybe 1 to 2 terabytes of data per second, but it has to read out 10 times as much. So these are very, very unique problems. These are not problems you can throw more hardware at. The hardware doesn't exist. The technology doesn't exist, and the skills don't exist. So these are everything has to be built, and that's why they really are looking to people of the world to satisfy this, to help them out. So these are just a couple of charts. One is for CERN at the top, the bottom is SKA. And if you take a look, this is an unfathomable amount of data. And they don't have the technology to process it all. So they're looking for full full stack data science stack solutions that can come in and have the ability, once the hardware catches up, to actually tackle these problems. And that's what we're working on in the Fort Collins lab. Power is not something that we are necessarily tackling because the power problems for these two configurations are so unique. CERN, once it's high lumen Hadron Collider is fully operational, it's going to require about 1 terawatt an hour. And if you put that into perspective, all of the United States last year used about just under 4 terawatts per hour. So it's a massive power problem that a lot of people think could never be solved outside of quantum computing. And but the other two problems, they really should be solvable. So those are the types of things that we're tackling. So all of these have to be put into a research format. You develop the question, can hardware, specifically HPE hardware in this case, open storage data formats, which is a special type. Basically, you're turning the data into a machine learning use case. And you're building intelligence around all of the data, such that the metadata aligns perfectly with the actual data so that you can continually update and run real-time processing on the fly. And then the neural network. So the question remains, will a Gen 2 artificial neural network actually work for use cases like this? The verdict is still out. We know that self-organizing maps have been attempted in the past, and they don't scale. So as long as the data set is small, they are quite successful with high-dimensional data. However, when you are dealing with very large data sets, then they the error rates increase there. So you have to basically create a hybrid neural network, which is what we're doing in the lab. And we're taking a look at k-nearest neighbor and k-means. And what this is doing is it's allowing clear lines of demarcation for the clusters. If we have very, very clear clusters, then we're able to get accurate predictions, which is really what's important to the work that we're doing there. And then the question that remains is, are we going to be able to actually create predictions when the model has never seen the data before? So we can train all day and night on petascale data sets, but is the model going to be any good for accurately classifying data that it's never seen before, which would be the type of anomaly that any of these astronomy use cases would be looking for? So if you think about SETI's Breakthrough Listen project, the bulk of that data is radio data, radio frequency data. You can't just exclude it, because the chance that you would also be excluding a potential interesting source, an unknown source, is quite high. So you have to be able to actually classify it, recognize it, and then you have to find a model that would be able to actually classify something that it's never seen before. It's never been trained on before. And this is not something artificial neural networks do. So then the question remains, are we looking at Gen 3 neural networks, which would be like spiking neural networks and imitation learning instead of reinforcement learning, such that it thinks like a human being? And the bulk of those algorithms and that math is still very much theoretical. So lots of math problems there. And then the data set. So these models have been very successful with terabytes, like 80 terabyte data sets. But we need to know if they are equally successful with multi-petabyte data sets, because the amount of data, SKA is going to be processing 200 petabytes of data per day once it's fully online. And if you think about autonomous, the automobile industry, they're looking at about 200 exabytes of data per year. It's all the exact same technology for the most part that's going to be processing exabytes of data. So you have to find the best algorithms that can do that. And I already went over this. So it looks like right now, where the world is at right now, they are processing and testing all this high dimensional data using a combination of supervised and unsupervised learning, and it's quite successful. But what we don't know is it successful once you hit petascale and beyond? And that's exactly what we are working to answer in the lab in Fort Collins. And so this real-time pipeline, this is exactly the pipeline that we're using with the celestial data set. And it's a challenge because all this data is different, and we're effectively building an AI fusion system. So we're taking a bunch of data, none of which looks alike, and we are intersecting it to find pattern matching, any similarities, to try and train the model to look for things that it's never seen before. So ingest, you're using different types of tools. Kafka is great for small packets, but a lot of these are images, which are really quite large. So we have to change the fire hose to something like Pulsar for images. And we use Flink for everything on streams because it's so flexible, it's so fast. And so there are things like that. We have to use specific ETL tools because you're moving massive amounts of data all throughout the pipeline at very, very high speeds. And for NoSQL, you have to have a NoSQL database that has the ability to do many millions of not just writes, but reads. And they have to be able to do those reads 2 to 10 times as fast as they do the writes. There's only one database out there that's been able to do this in my lab, and that's AeroSpike. And then the hardware. So you basically match all the software with precision-based hardware. So we do a lot with CPU whenever we can. However, we've got some pretty high power because we have to do a whole lot of horizontal scale. GPUs, even higher power if we're not careful on what we're doing. For instance, all these SOMs, it's high dimensional data, so it's very, very high resolution. It's a lot of power. So I have to code very, very creatively a lot of times just to cut power. Power, just like performance, is a firm number. The client gives me, it does not budge. And so this is something we have to be incredibly sensitive to. Almost all the code is done in Python. It's done in C. If it's HPC, it's done in Fortran or C, C++. And that's just because if you put Python on the HPC gear, it's orders of magnitude slower. So, you've got like 2 orders of magnitude performance loss between Fortran and Python. And so it's things like that if you're doing numerical computations. You have to know the data, you have to know the code, you have to be able to build across the entire stack. So at the front end, it's probably going to be Java because Java is very, very fast at that, at those user portals and those web tiers. But then at the back end, it's probably going to be Python for all of your model development. But then HPC is usually not Python. That's usually going to be C or C++ or something else to truly saturate that really expensive gear. So you have to have all these skill sets, and you have to know exactly what tools you can build all the way across that stack. So this is a picture of Fort Collins. We pretty much use everything. It's an open source R&D lab. We solve every single problem with open source. If we cannot solve it with open source, then and only then will we branch out into commercial software. And that's actually how AeroSpike came in there. As I worked across the NoSQL open source gamut, and I could not hit the numbers that I had to hit for the high dimensional use case for astrophysics. And so it's little things like that. We swap in, we swap out. We don't OEM any of this work. Everything we can give back to the community, it goes right back to the community. The math, the code, even the collateral. So, and that's pretty much it. And we basically work to build one stack. It's the developers built it on their laptops. It rolls to the edge, to core, to cloud, wherever the client needs it to go. So I don't like to use the word agile. I think it's overused. I prefer the word flow. So it just has a singular flow. Everything runs in a container, and it moves through Kubernetes or Mesos, however they want to control it. So thank you.